Okay, as you can see here, this is some of the problem example. Okay, so for today, I will be focusing on this one, tipping due to friction. So if you are wondering what is tipping, so for example, if we have this kind of problem, okay, this is a problem of a crate, okay, a crate or a wardrobe or anything, okay, then if you try to push this kind of crate, okay, like what this person did, okay, pushing the crate, okay, what do you think will happen there? Any of you here, I believe some of you here already tried it already to push a wardrobe or crate or things which is quite tall like this. Okay, what will be happening if you pushing it like what the person did here? Any of you have any idea?
Friction, Pak.
Friction.
Friction to the left. Yes.
Friction to the left. That's all. Derajat. That's all, Derajat.
Contact force from the hand, Pak.
Contact force from the hand. Okay. But has any of you encounter this kind of thing? When you push it like this, then the crate tips. What I mean by tips means it rotates instead of having a translational movement. Okay, the crate, instead of having just translational movement like this, moving like that, okay, instead of like that, but it tips at this tipping happening. So it means like it rotates at this center of rotation like this and fall like that. Has it ever happened to you guys? Any of you here has ever encountered this kind of a problem or not?
Yes, sir.
Yes, sir.
Yep. Okay. So some of you, I believe it happened to some of you. But can you explain to me what caused that problem? Because basically, if based on the things that you learn from physics, basically, if we draw the free body diagram of the crate, it will be like this. Then the normal force will be like this. It's normal force. This is the weight. And this is the pushing force from the man, Kp. And then there will be a friction force like this, right? What will cause the rotation then?
Yang ganjel.
Because of the
Ada yang ganjel. Okay. What
Mantap, like.
ada yang ganjel? Okay. So something is adding the friction, right? So up until now, okay, actually the things that have been taught to you guys about friction is about a point friction. What I mean by point friction is we assume one particular things like a box or a mouse or something like that, which we try to analyze, okay, which we try to analyze. For example, we have a box like this, then we try to analyze if we give a force to the right, what will be happening there if the box has weight of W. So of course it will have a normal force due to the weight, okay, and then there will be a friction force which resists the movement, something like that, right? That's what the things that you have learned up until now. But remember, this kind of thing, we consider this as a point, okay? It's point equilibrium. Okay? But not all the things and not all the friction problem, we can solve it using point equilibrium, okay? So this is one of the case, okay? If we have case like this, we can't solve this with point equilibrium. Why we can solve this with point equilibrium? Because if actually the crate is not tipping, right? And you're pushing it to the right and it's not tipping. But if you take a look at this free body diagram, right? Okay, the friction force there, okay, there will be a friction force, normal force, W, okay. If you calculate the sigma moment, okay, sigma moment against this particular point, okay. For example, this point, we name it as A. Sigma moment at A equal to 0. It's supposed to follow this equation, right? But if you take a look at that, you can see here, the W, the line of action is actually going through A. So there will be no moment because of W. Then friction force, it's happening at A as well. So there will be no moment due to friction force. Normal force, it's happening at A as well. So there will be no moment due to normal force as well. The only moment there will be this, due to P, right? And this is the moment M. The height there will be the moment M. So in this particular free body diagram, our sigma moment at A equal to 0 will not be able to be fulfilled. Okay, so it's a big problem. So why we can't fulfill this particular equation? Because the actual things which is happening at this particular rate is actually not like that. Okay, it's not like that. Okay, so basically the correct free body diagram is not like this. This is the wrong free body diagram. So remember, this kind of thing is a wrong free body diagram, this one. So you are not supposed to use this. Okay, so what we supposed to do then? So this is the correct one. You can see that, right? If P, we give P at the height of H here, then we have W, then we have normal force, then we have friction force, okay? The difference between this particular free body diagram and this particular free body diagram, okay, is at this, the normal force, the location of the normal force. You see, right? The left free body diagram, the location of the normal force is exactly at the same line of action as W, which is wrong. Okay, why? Because this is not a point equilibrium anymore. For this one, the right free body diagram, the normal force is the normal force is given at distance x. Okay, at distance x from the center line or the line of action of the W. The distance there is x. Okay, why we have to have this distance x there is because of the equation that I talk about just now, sigma moment. In order sigma moment equal to 0 to be fulfilled, okay, the normal force is not supposed to be in the same line of action as W, because it will not give us any torque. It will not give us any moment. Okay, but if you do it this way, if we draw it this way, okay, and we calculate the sigma moment at this particular point, for example, or not this particular point, but at this particular point, for example, just now, the same at point A equal to 0, okay, due to P here, there will be P multiplied by H clockwise, okay, and due to N here at the bottom, there will be N multiplied by X counterclockwise equal to 0. So we still can fulfill this particular equation, sigma moment at A equal to 0. That's the thing. So basically, if you have this kind of problem where we can't assume point equilibrium anymore, okay, we have to make sure that our normal force is at the correct location. Or if it's not known yet, you have to assume that the normal force has distance, certain distance from the line of action of the W, like that. That's the thing about it. Okay. Until this point, anyone want to ask question, please? Rajat, do you understand?
Yes, sir.
Okay. How about Rafi? I haven't heard from Rafi yet. Rafi, where is Rafi?
Sir.
Yep.
Can we put the N itu jadi kayak terserah gitu ya, Pak? Maksudnya kayak di kiri di kanan itu tetap boleh.
No. If you put N on the left, okay, the moment there will be the same direction as the moment due to P, right?
Yes.
So it will not be able to be balancing it out. If you put it there, later your X value will be negative.
Oh.
So it will be pushed to the right again. So at the end, your N location will be at the right like this. Okay, because this one and this one will supposed to be in balance condition. The moment due to normal force and the moment due to the pushing force, it's supposed to be in balance condition. You understand what I mean?
Understand, Pak.
Okay. Any other one to ask question about this? Rafi, do you have any question? Oh, there are several questions in the group chat. Okay. So how to determine X? How to determine X is just by solving this particular equation. So most likely, if we have problem like this, okay, most likely if we have problem like this, either the H or the X are known value already. Okay, so in that case, if P is known value, H is known value, then N, the value of N using sigma Fy equal to 0, we can get that Y is equal to N. Then in that case, N is known value as well. Multiply by X equal to 0. In this case, X will be very simple, right? X will be P multiplied by H divided by N.
Okay, thank you, sir.
Yep. Okay, and
Excuse me, sir.
Who's this?
It's Manaf, sir.
Okay, Manaf, yeah.
Jadi kalau yang N distance X itu kan apply kalau ada satu force saja kan, yaitu P dari kiri kan, Pak. Kalau dia misalnya ada satu force lagi dari kanan ke kiri, kan itu bisa jadi balance. Berarti N-nya nggak perlu pakai X lagi gitu.
Yep.
Atau tetap harus pakai?
Yeah, yes, of course, if you have a P on the left and P on the right as well, at the same height like that, it will be in balance, so you don't have to put the N as well.
What I mean is kalau ada force lain dari kanan ke kiri.
It depends. If the force is not yet balancing the moment due to P there, okay, like it or not, the N supposed to be in the X direction from the left as well in order to balance the moment like it. Okay.
Okay, Pak. Terima kasih, Pak.
Yep. Any other question? So basically, the things that I told you today is a condition where point equilibrium is not, it cannot be applied anymore. So point equilibrium cannot be applied when the H like this is known. Okay. The dimension if the dimension is big enough to be neglected. In that case, yes, we can't use point equilibrium anymore. Point equilibrium can only be used if, right? Point equilibrium can only be used if the things that we studied about is very small. So although we put the force at the center like this, okay, the moment there due to the moment due to the force, okay, is negligible because the things is very small. But if the dimension is big enough, like this, right? The dimension is big enough, and the dimension is known as well. The height is the height is there. The height there is known as well. In that case, you can't neglect the dimension. In that case, you will not be able to use point equilibrium anymore. Because you can't use point equilibrium anymore, okay? You have to add another equation, another equation. Another equation there is supposed to be our sigma moment. Okay, because for point equilibrium, we don't have sigma moment. Okay, for point equilibrium, we don't have sigma moment. I told you from the beginning, right? For point equilibrium, we don't have sigma moment. Okay. If there is no question about this, then I will continue. Hey, wait. Just now, I think I remember that you have some of you have question in the chat. Okay, from a moment. Point A. Okay. Maufi. Okay, thank you. Sir, how to determine point A? Is it at any point? Yes. Point A is supposed to be at any point. It can be at any point. Okay. Well, I mean, the sigma moment, the sigma moment is supposed to be there. Sigma moment equal to 0, right? This particular equation is supposed to be fulfilled for any point in the free body diagram. Can be any point. Okay. I choose point A just because at point A we can make sure that the moment which is caused at happening at point A is just due to P and normal force in order to explain the location of the normal force. That's all. Rafi, why you keep watching television? You're supposed to listen to me. Okay. Any other question? If not, I will continue with the next one. Okay. Now, the next thing that I want to discuss about is the tipping condition. Okay. Remember, right? If this is the case, right? If this is the case, if somebody pushing the crate with a force P like that, and then if there is a no tipping condition, I mean like the crate instead of rolling, it still move forward like that. So the free body diagram that's supposed to be there is supposed to be like this. Okay, this is the condition where tipping is not happening. But remember, if tipping is happening, okay, what is actually happening there? Okay, if tipping is happening, right, the free body diagram is slightly different. Let me wipe this one out first. If tipping is happening, the free body diagram is like this. Okay, the free body diagram is like this. The only difference between the middle free body diagram and the right free body diagram is the location of the normal force. Okay, as you can see there, okay, the location of the normal force of this particular free body diagram, this is the free body diagram of the crate where the crate is in balance condition or moving in constant speed horizontally like that. Okay, but if it's in tipping condition, this is the free body diagram. The only difference there is the location of the normal force. okay, if the location of the normal force is at the edge, okay, at this particular edge, okay, it means that tipping is about to happen because we can't make X bigger anymore. Okay, if the location of the N is at the edge like this, right? Okay, it means that tipping is about to happen. Okay, tipping is about to happen because we can't make X bigger anymore. Okay, and if you calculate using the previous equation that I gave you, sigma moment at point A, right? Sigma moment at point A, it's supposed to be P multiplied by H minus N multiplied by X. In this case, our X value is supposed to be P multiplied by H divided by N, right? If this particular value of X, right, is the same as the distance from this to this, right? Which means that the location of the normal force right now is at the edge like this. That particular condition, we call it as tipping about to happen. Then, if the X value, okay, for example, in this case is B over 2, right? If the X is the value of X from this particular calculation, right, is equal to B over 2, this particular condition, we call it tipping about to happen. But if this one is happening, okay, X is bigger than B over 2. This case means that tipping is already happening because it's not supposed to be happening there. I mean, because it's not supposed to be there. It's not possible to happen. Okay, this kind of thing is not possible to happen. Why? Because if X is bigger than B over 2, yeah, the normal force is supposed to be here, right? Which is not possible. Okay, in that case, it means that our free body diagram is wrong. In that case, it means that the tipping is already happening. That's why we have to change our free body diagram. So the free body diagram is still like this, but the calculation, okay, the calculation is supposed to be rotational movement calculation like that. Okay, until this particular point, anyone want to ask question? Please. It's about tipping, right? Victoria, do you have any question?
No, sir.
No. Okay. Where is Abiyat? Abiyat is not around. Okay, and just now, Rafi Salahuddin, where are you? Seems like you are not listening, right? Okay. Anyone want to ask question about this? About tipping condition? Nope. No question? Everyone understand? Okay.
Yes.
In that case, I think I will continue again. Okay. So basically, if we have a problem like this where point equilibrium is not applicable, which means we have to use sigma moment, sigma fx, and sigma fy. Okay, you have to check as well whether tipping is happening or not. Okay, so as I told you, okay, tipping is about to happen when x here, when the value of x here is the same as b over 2 for this particular case. Okay, and tipping is happening if the calculation of x give you results bigger than P over 2. Okay, that's the thing. Okay. I'm a little bit wondering why you don't ask me a question about why suddenly the normal force can be put over there. Okay, I think I will explain to you the basic behind it. Okay, so whenever you have a something like this, right, and it has weight like that, okay, if you see this kind of problem, okay, and if you want to draw the free body diagram, normally what you draw is like this, right, normal force like this. Okay, but if the actual condition is the crate, if the crate is put at the top of a ground like this, actually the actual condition is not like this. The actual condition, even though this one is a correct representation, although this free body diagram is the correct representation of the problem, but there is a simplification there. So the actual condition there is supposed to be like this. W, but at the bottom, it's supposed to be distributed force. The force is distributed over the area of the ground, over the area, the contact area between the crate and the ground, like that. Okay. So when this condition is happening, okay, the distribution is supposed to be constant like this. Constant distribution. The distribution is supposed to be constant like this. Okay, but if suddenly there is a obstruction in terms in the shape of outside force P like this, okay, the distribution will not be like this anymore. It will not be constant anymore. Okay, so the distribution most likely will change into like this. Roughly it's like this. Something like this. Okay, remember, right? When I told you about the distributed force, right? We can represent the distributed force with a concentrated force in the free body diagram. For example, like this, if the COG of the concentrated force is over here, we can represent this particular distributed force with normal force exactly in the middle like this. Okay, but for this kind of problem, okay, the COG most likely is not exactly in the middle, but slightly on the right. Slightly on the right like this. Okay, so it's P. That's why when we have to draw, okay, that's why when we have to draw the free body diagram beside friction force, okay, this one is beside friction force, there is a friction force as well, okay, that's why when we have to draw the representation of the free body diagram, we have to draw it like this. P, W, then friction force, then normal force. But the normal force is not exactly in the middle, like this one, but slightly on the right because the center, the COG of this particular distributed normal force is slightly on the right, something like that. So that's the basic behind friction problem, this kind of friction problem. Okay, when you have this kind of friction problem, the things that actually happen is actually like this, but you can represent the distributed force here with this, and you can represent the distributed force here with this one, and the location is slightly on the right. This is X distance there. Okay, Anyone understand about this? Anyone have any question about this?
No, yes, sir.
Not yet. So still okay, right? Good.
Yes, sir.
I want to check again with Rafi. Rafi is still there or not? Or still watching TV? Let me check.
Yes, sir.
Oh, you are listening to me. Okay, good.
Yeah, but my internet connection is kind of slow. So
Okay. I thought you are still watching TV.
I'm not sure.
Okay, good. Anyone here want to ask question about this? If there is no question, I think after this, I will give you one simple problem example and then another two problem example before we conclude the class today. Rafi, I want to ask you about the previous exam. Can you do the previous exam, Rafi?
Not really, sir.
Not really. Okay then. Try your best to
just do
study
it.
for the final exam. Okay. Yep.
Okay.
What did you say just now?
I just do what I can do.
You give up?
No, no, no. I just do what I can do.
You just do what you can do. Okay, good. Okay, if there is no more question about this, the basic about the tipping condition, then I will continue with the problem example on this. Okay. So the first problem example is the simple one. For example, I have a box. Okay. I have a box like this. I put the box on top of the ground. Okay. And then I know that the weight of the box is 100 Newton. Okay. Then I give a pushing force P. So the dimension of the box is like this. The height of the box is 1 meter. The width of the box is half meter. Okay. And the center of gravity is exactly in the middle. Then I give a force, pushing force P, which is equal to 20 Newton at the height of 0.7 meter from the ground. Okay. The things that I know is the static coefficient of friction is 0.4 and the kinetic coefficient of friction is 0.2. Okay. The question here is what is happening to the box? Okay, whether it stays stationary or it's moving translationally to the right, or it rotates due to tipping. Okay, this is the problem, the first problem example that I want to discuss about in order to teach you guys about tipping condition. Okay, for this kind of problem, as usual, we have to draw the free body diagram, right? And this is the free body diagram. Okay. the center of gravity is exactly in the middle. So the W is supposed to be here, 100 Newton. Then the pushing force is 20 Newton around here. Then what we have here, there's supposed to be a friction force. Okay, and beside that, we're supposed to have as well normal force, right? And there is supposed to be distance here, x, from the line of action of the W. Okay, I believe this is the complete free body diagram. Then we can try to solve it. Okay, we can try to solve for N and friction force first using sigma Fy equal to 0 and sigma Fx equal to 0. Using sigma Fy equal to 0, if going up is positive, then what we have will be N minus 100 Newton, supposed to be 0. So our N, normal force, supposed to be equal to 100 Newton. Okay, then using sigma Fx equal to 0, okay, the horizontal force which is happening there is only 20 Newton to the right and frictional force to the left. If to the left is positive, what we have will be F minus 20 Newton, supposed to be 0. So our frictional force is supposed to be 20 Newton. Okay, but if it is just a point equilibrium, which means the dimension is not there, the height is not there, the width is not there, okay, this kind of calculation is enough. So we can conclude there, if it's point equilibrium, we can conclude there that the condition is in, the grid is in a static equilibrium, so it's not moving at all, okay, and the frictional force is 20 Newton, okay, but remember, this one is not point equilibrium because the dimension is known, this, and this. So we have to check for another condition. What is the other condition? Is the location of X, in order to see whether tipping condition is already happening or not, or is about to happen, or not happening at all. Okay, so we can check by calculating for X. How to calculate for X? We can use sigma moment. Okay, same as before, I will use this particular point A here. I name it as point A. Sigma moment at A equal to 0. Okay, if I use sigma moment at A equal to 0, okay, the moment due to 100 Newton here, the weight 100 Newton there will be no moment due to this. Okay, there will be no moment due to the frictional force as well. So the moment there will be caused by the normal force and the 20 Newton. Sorry, 20 Newton. Okay, if clockwise is positive, so what I will have will be 20 multiplied by the height there is 0.7. Okay, this one. The distance from the ground, 0.7. Okay, clockwise. Sorry, I think there is a problem. I will continue again. Why? What is here? Stop share. Sorry. Okay. Let me share again. Yeah, this one. Yep, this one. Okay. Sorry for the problem just now. So the moment due to 20 Newton will be like this, and the moment due to the normal force is supposed to be counterclockwise, right? And the value is supposed to be n multiplied by x, and the value of n is 100 Newton, equal to 0. Okay, that's why we can calculate for x. The x here is supposed to be 20 multiplied by 0.7 is supposed to be 14 divided by 100. So x there is supposed to be 0.14 meter. Okay. Now let's check whether 0.14, the location is already outside of the box or the crate or not. Okay. Remember, just now the width is 0.5 meters. If the width is 0.5 meters, the distance from A, okay, the distance from A to the right edge here, this one, it's supposed to be 0.5 divided by 2. Okay, so this one is our B just now, right? So our B per 2 is supposed to be 0.25 meter. Okay, and in our case here, the X is still smaller than B over 2. That's what in this case.
Ada di momen-momen di mana gue lama di jalan, gue bosan sama musik-musik yang.
Who's putting the radio just now? Okay, so the X there, the value of X there is supposed, in this case, is less than B over 2. So in this case, we know, right? We know that the X is less than B over 2. That's why tipping is not happening yet. So the condition, we know that the condition is there is no movement. The first one is there is no movement at all. Everything is in static equilibrium. Okay. The second one, the friction force which is happening is equal to 20 Newton. The third one, tipping is not happening. No tipping. That's the thing. This is the first problem example. Anyone want to ask question about this?
Pak.
Yep.
Sorry, can you repeat for the first point? What is that? The first point again? There is no movement.
The first point is no movement. No movement means that the static equilibrium is there. Because like this, right? The friction force, actually I forgot about doing something else. The friction force here is 20 Newton, right? And we have to, in order to check for the number one, whether there is a movement or not, actually, we're supposed to, I forgot about this, I'm so sorry about it. We have to check for the maximum friction force which is available. The maximum friction force which is available is supposed to be what? Normal force
time normal
multiplied by
force
mu
US,
right?
By N.
So in this case is 100 Newton multiplied by 0.4.
0.4.
So in this case is 40 Newton.
40.
Yep. The maximum frictional force is 40 Newton. So our frictional force which is happening, 20 Newton, is still lower than the maximum frictional force. In that case, we know that the static equilibrium is there. So we know that the crate or the box is not moving at all.
Oh.
No movement. Okay. Number two, the other condition that we know for number two is the fraction. What is the value of the friction coefficient? Friction force is 20 Newton. And number three, okay, because of this, right? Because X is still lower than P over 2 in this case, okay, no tipping. Okay, those three conditions, we know it already from all of this calculation. Okay, any question there? Any question there? Sir, so for now, we have to draw the ground as well. Nope, nope. Better not. You are not supposed to draw the ground. Okay. You are not supposed to draw the ground in the free body diagram. So for this one is the known. This one is the problem. Okay. This one is the problem. That's why I draw the ground. But this is our free body diagram. That's why in this particular free body diagram, I don't draw the ground. So whenever you draw the free body diagram, you are not supposed to draw the ground. You just concentrate on the systems that you want to concentrate on. Any other question? Yeah.
Pak.
Yep.
Itu kalau normal force-nya pindah, berarti friction-nya juga pindah dong poinnya.
Oh, yes. Actually, the friction force is supposed to be happening at the same point as the normal force. That's the easiest logic that you're supposed to follow. So it's supposed to be happening at the exact same point.
Okay.
Yep. Any other question? Answer what happened with the distribution force. Okay. Maufi. Okay, Maufi Mirza. Yeah. The distribution force just now, the things that I talk about just now, right? Not just now, but the previous one that I talk about. Okay, this one. Okay, this one we don't have to draw for the distribution force. We don't have to draw for the distribution force. So this distribution force, why I draw it like this, is just in order for you guys to understand why the normal force is in the middle for this particular case, and why the normal force is slightly on the right on this one. Okay, something like that. So basically, what you're supposed to do is just to draw the representative concentrated force only. You don't have to draw for the distributed force for the normal force. Okay, you don't have to draw that. You have to draw only the representative concentrated force, because that one is enough. But why I draw it like this is just because I want to tell you guys why the reason behind why this one is in the middle and this one is slightly on the right, like that. Okay. Okay, good. Any other question? Because it's already 2 p.m. Okay. Sorry. So yeah, I think I will discuss a little bit about some other problem example. This is another problem example which is quite easy as well. This one. Okay. This one is another problem example which is quite easy. The problem is exactly the same as before, but for this one, the contact is only happening at A and at B. The contact is only happening at A and at B. Okay, so for this one, I think because it's already 2 p.m., what you can do is try to do this particular problem. Okay, try to do the problem 9:45 by yourself. Okay, tomorrow when we start our class, okay, before I discuss about the wages, I will start about the discussion of this particular problem first. So before I discuss about the wages, because tomorrow we have 2 hours, right? We have 2 hours from 1 p.m. till 3 p.m. Okay, I will start with discussion of the this particular problem before I continue with the concept of the wages. Okay, wages we talk about is not wages that you girls normally use, but this is the wages that we normally use to implement the friction theory. Okay. If there is no more question about today's class, I think I will end today's class. Okay. Anyone have any question before I close up today's class? Malfi, do you have any question?
Not yet, sir.
No. Okay.
Pak, sorry, Pak. Last one question.
Yeah.
Can you just give us like a brief explanation, like what is tipping exactly? Like, I'm still confused about the definition of tipping.
Oh, the definition of tipping. That's why from the beginning, right? Abdul Malik, right?
Yes.
From the beginning, I asked you whether have you ever pushed a drawer or a wardrobe or box like that, and then when you push it, okay,
it rotates.
Suddenly it rotates, right?
Oh. Okay.
Have it ever happened to you?
Yes.
Tipping is like that.
Oh.
That's the definition of tipping. When it rotates, it's tipping is happening there. Okay. So what actually happening when tipping is happening, okay, is the location of the normal force when you calculate is on the right of the edge. So it's outside of the box already, which is not supposed to be happening, right?
Oh, okay. That's
why instead of static equilibrium, the dynamic equilibrium is happening in there. Not dynamic equilibrium, but I mean like there will be a movement there, like that. Because static equilibrium cannot be fulfilled anymore. That is tipping.
Okay, sir. Thank you.
Yep. Any other question? Mac Farrell, do you want to ask question?
Enggak, Pak.
Okay, good then in that case. I think if there is no more questions, anyway, one more. Sir, it's Malfi, right? Just now you asked me about this, right? Okay. If there is no more question about this, I think that's all for today. See you guys tomorrow at 1 p.m. Okay, remember 1 p.m. sharp, and we will. I will start discussing about the problem that we talked about just now. And one more thing, don't forget to mark your attendance in the attendance list. Okay.
Terima kasih, Pak.
Akademik ITB ACD. Okay, ya, sama-sama.
Terima kasih.
See you guys tomorrow. Yeah. Bye.
Terima kasih, Pak.